this in with the electro CO2 catalysis guys and another group meeting. In this week, I'm gathering some additional physical data, but the slides I haven't yet updated. So the key question is that for CO2 catalysis, there has been like about, say, when I was talking to the CO2 electrocatalysis guys, including the
Mm,
ones in our group and the ones elsewhere, people has actually kind of already lacks the enthusiasm to develop new catalysts. There are reasons behind that. What I think the first reason is that there is no existing techniques that allows high throughput ECO2 RR electrocatalytic exploration to date. If you want to make like ternary and make a DOE table, it's going to get crazy to make that, and there's no method to do that. And another second thing is that so even if somebody just tried to do it low throughput, prepare a few samples, it's highly likely not going to be as good as the binary samples, which are highly optimized. So eventually it comes to the throughput of making and throughput of testing. So I'm working on the throughput of synthesis side, and there are Fanshu who is working, Fanshu and Wang Yu who is working on the throughput of the testing side. So there are development that's going on for both. So so let's look at the pipeline of what we currently are thinking about in mind. So let me just have a pointer here. So we have like a few options in mind. So the first is the low temperature carbon thermal shock synthesis. I'm going to present a bit later today. The second is a few months ago, you guys see it, and currently it's being built by our automation expert Ali. It's not Alibaba, just for clarification. So we're expecting this setup to be ready in about a month or something. So I can focus a bit next on this one. So this is the top priority and it's the second priority. And we also have some other considerations in mind. Currently, there is a new microwave synthesis, which is not solid state microwave synthesis, but a wet chemistry microwave synthesis. We will be engaging the suppliers tomorrow and ask for their potential recipes, connections, and application notes. And there a more conventional method, but say spirit coating plus gel-based vapor deposition. I had a chat with Chenghua. However, apparently, as you can see, once we introduce vapor deposition, the elemental ratio control will not be directly relevant to the precursor we put in. So that is the key here. So according to the difficulty and easiness of achieve, we rank it by 1, 2, 3, 4 different options here. So, and for electrochemical CO2 reduction, currently we're trying to build up a baseline against the state of art, not the state of art, a standard copper catalyst, which is like alignment catalyst, say elemental copper or elemental silver for a lot of places to investigate for copper 2 that carbon 2 that is copper or copper 1 CO that is silver to establish the baseline. So currently we are in the stage of doing baseline for number one option. So the preparation is very simple. Actually, a lot of people in a group can do this very, very fast than I do. So first we prepare the precursor solution mixture. We spray coat the solution mixture over the substrate, and then we need to dry it overnight to ensure it is 100% dry status on a heating plate about 80 Celsius degree. So after that, we did a lot of people has used the script I have been writing. It has an automated calibration and the sample loading and mounting. It is basically being pushed by a time bar, and so each of the sample need to be finished in 90 seconds time. And then the thermal shock will also be arranged by the program I have done. So, and after that, we will quickly do a hydrophobicity test to see whether the sample is hydrophobic to prevent a flooding, which is the electrolyte penetrate through the catalytic sample going through the gas chamber. And if this is okay, then we will think that, okay, this sample is a bit more likely for ECO2 reduction test. However, in this stage, we will be slightly more cautious because all this experience are from like previous process from magnetron sputtering and spray coating, where people do not have direct material synthesis in the material preparation. And here we have a direct material synthesis in the material preparation loop. So we will need to waste a few more samples to verify that yes, low hydrophobicity means low performance. And we need to verify in both cases, in the substrate cases and in the corporate cases, and hopefully also in the precursor cases, which is maybe slightly a bit later. So if there's any issues, we can consider optimizing, of course, the carbon thermal shock parameters, the spray coating pattern, how we do spray coating, and also if there is something very specific we understand, we can do some surface modifications. But this one has already been said no by an expert. She says that plasma etching, she also was like me, tried everything, all the plasma, O2, N2, argon, etc., and all this increased hydrophilicity. So lowers, increase hydrophilicity. So lowers hydrophobicity. So it doesn't really make sense. So with this, it is pretty easy to achieve, say, about 25 to 30 samples a day. And but as of now, our baseline is not established. So it's not really the time to go to the high throughput making and testing. Instead, is trying to use this technique to probe what is the best range of operation conditions and go further. So here we make a 12 sample DOE table. So let's just forget about this table first. And let me show you something in the end that what we trying to understand from this, why we need to build this DOE table. The first is that we need to have a few questions to answer. And previously, we were never able to know this from two reasons. The first reason is although I was trying to prepare a sample and there is a person trying to test the sample, however, typically when the testing starts, the sample has expired for like 3 weeks already. So the testing capability wasn't really ready. That's number one. And second is even when the sample is being tested, we have no idea how much degradation has happened. So that's two of the key problems. And an additional thing when I went through the collaborators lab is that every time the cell and the electrolyte containers, all these sort of things slightly changed every time. So I'm not an expert, but this looks to me like that. So the experimental testing conditions, I have doubts on whether the data are cross-comparable. So there are quite a few things that I have doubt on the previous data. So for this time, we will need to establish a consistent testing standard from 0 to 1 and ensure it is the same all the time. So we need to answer these few questions. First is, what is the carbon thermal shock due to the substrate? The substrate has a hydrophobic layer on top, and we need to clearly know what does this do to the hydrophobic layer. And when this is doing to the hydrophobic layer, does this increase the exchange current density when we are doing the HER activity? I mean, because it has no copper on top, so it is probably not going to reduce CO2, but it is maybe likely going to change the current density. That's the first one we need to understand. And the second question is, what is the carbon thermal condition range, time and temperature in this case to ensure the minimum hydrophobicity and no flooding? So I think after some basic tests of the samples, maybe no need even to test the product, we'll be able to know about this. And the final one is the correlation we are targeting at. Maybe not all the samples, but maybe not all the 12 samples, but maybe say the left 8 samples is pretty critical here because the right samples, there is a high chance to lose. We can test like 1 or 2 eventually, but the left 8 samples pretty critical. And we won't be able to understand the correlations between the precursor conversion rate, the carbon thermal shock conditions, all these are the input parameters somehow, and how it links to the output hydrophobicity, and finally link to the CO2 sensitivity and partial current density. So these are all the know-hows for this workflow that will help us to establish the baseline. And we also need to
All right.
cross-compare the same.
I mean, most people will not understand this. because it's too detailed for them, right?
All right.
But yeah, makes sense. I think any questions about this, guys? Like basically, Ivan's looking at a new synthesis technique with lower temperature carbothermal. I think that's the key take home message, using
Yeah.
different precursors. And then we are able to try to put it on the substrate, but the substrate can change, the property will change. It's a difficult problem he's trying to
Yeah.
solve.
How is drying? Like overnight drying. What do you mean?
Yes, it's just putting the substrate on the heating plate for overnight.
Mean oxidation, whatever. Is it okay? What would you?
For this specific application, oxidation, when I talk to the experts and see their data, it doesn't really matter.
Okay.
Even their nanoparticles, pure copper,
Uh,
metal, they never stored it in argon glove box. They just put it in air.
yeah. I mean, there's another way, like people do in chemistry,
Yeah.
like removing the solvent is like nothing but a small desiccator, like vacuum desiccator. Uh,
Oh, that's very nice. That's
yeah.
very nice.
Uh,
That's very
Actually,
nice.
yeah, the solvent evaporate, and you will not get any other oxidation, other things.
Oh,
Uh,
this is very
a
nice.
small hot plate in vacuum desiccator is definitely will be helpful
Yes,
than
yes, yes, yes,
just
yes.
drying. Yeah,
Yeah.
should vacuum itself is removes
Yeah,
the solvents. Yeah.
yeah, vacuum itself.
Okay, we need to have a chat about this a bit later. I don't really understand this technique much. Yeah,
We did long time before
yeah,
when you dry the nanoparticles. Suppose
hmm
once you synthesize the nanoparticles,
this is helpful.
there's some solvent always.
Yeah,
So we generally keep in a vacuum desiccator
yeah,
to remove the solvents. Yeah.
yeah.
Yeah. I mean, I'm also new to this.
Yeah, I mean, it could be something because one thing Ivan mentioned to me yesterday was that the drying may result in the non-uniformity. Is it possible, Ivan?
So actually I should take a few pictures after the drying, but I couldn't see it. So the key is that I need to find a method to characterize the uniformity after the drying. I should see, but by right it shouldn't because the way how I do spray coating is I have like say a 80 Celsius degree heating plate
Yeah.
and I spray coating it really really slowly to ensure that every time I spray I pass through it, it will dry in like about 10 seconds. And
Mm.
then I spray on top again another 10 seconds. So basically the uniformity, elemental uniformity achieved on the substrate is because I repeat it on the surface, say about 100 times, and all these are random.
Oh
So it
man.
is unlikely that the liquid can flow on the substrate. It is hardly likely because I'm spray coating very, very slow.
Yeah.
And I ensure it's spray coat on top, it dried. Uh, the reason I still dry it overnight is even though like on 80 Celsius plate, it looks dried, but there are still some like functional group or whatever, or some more highly coordinated water or ethanol that need overnight drying. It's just to kill the final 1% of things because previously I know it's going to kill the metal nucleation. So that's why we still keep drying overnight. And this is not the purpose of like drying the 99% of the solution. The 99% of the solution is already dried within like about 5 to 10 seconds.
Mm. Oh,
The
and sorry, I didn't
okay.
understand what the hydrophobic. You don't want hydrophobic, or you want to be
I
hydrophobic?
want, sorry, I actually I didn't give the context for you here, which
It's
I'm doing
fine,
slightly
fine. Tell
bad.
me. Yeah.
Yes. So the key is that here we are doing electrochemical CO2 reduction.
Yeah.
And say on this surface there is catalyst with electrolyte, and on this surface there is CO2. So you
Mm-hmm.
need gaseous CO2 to diffuse to the surface of the electrolyte for the
Mm-hmm.
electrochemical reactions to happen. If this surface leaks water, which
Yeah.
means hydrophilic, right? What happens is
Mm.
water will penetrate through, flooding the whole gas chamber. So
Yeah.
CO2 cannot directly contact with the
Mm-hmm. Material
with the
catalyst.
catalyst.
Yeah.
So then what we can only hope is that there is only a thin layer of water that can only diffuse some CO2. Actually, there are still some people doing that, but it is not something mature.
Mm-hmm.
So if this is fully flooded, then it does not happen. So conventionally, how this was addressed is that we buy a carbon paper coated with PTFE, so
Mhm.
it is hydrophobic, right? And
Yeah.
then you buy nanoparticle from Sigma Aldrich or
Yeah.
whichever and spray coated, or you prepare magnetic sputtering target and coat it. But all
Right.
these are like you understand, either you need to buy from somebody the nanoparticles, or you need to have a pre-made target, which is not something very fast. So basically very much limited the capability of combinatorial
Yeah.
research. I would say it's no till now.
Okay, cool.
Yeah.
Got it. Yeah, Kedar, go ahead. Yeah.
No, I mean, I was thinking, anyway, let's try it because let me leave the thought for later. I mean, once we try the electrochemical test, we will actually know what's going on.
Yes. And now I think the thing is, as you just mentioned, that they had, so we need to prioritize some of the samples
Yeah.
and also add a bit more physical characterizations for sure.
Yeah.
Yeah, so that's some adjustment, but I think the major workflow we have it here already.
Yeah.
So additionally is about the in-flight sintering. So I'm not sure if I showed this in this group. So previously we have the hydrophobicity issue. The reason is that we use carbon thermal shortcut, which is going to heat up the substrate. But now we don't heat the substrate at all. What we do is we have a syringe pump pushing the precursor solutions through an ultrasonication nozzle, and we spray coat the micro-sized droplet particles directly as a stream through a 1000, 2000, 3000 Celsius degrees carbon thermal shock mini furnace, and then it's ready, coat it on top. Previously, we have a version 1 and version 2 already. So we understand what are the problems. And currently we're trying to get to version 3. And the key here is that we need to maintain each of the surface temperature here, IR3 here, IR2 here, IR1. So 3 temperatures and 2 distances here, D1 between this surface and this surface, and D2 between this surface, very carefully, so that we are able to achieve controlled deposition of the metal nanoparticles on the surface. And because we have a water cooler here, so the surface shouldn't be too hot. The PTFE decomposition temperature is at least like 200 plus Celsius degree. With the water cooling, I talked to Ali. I mean, it doesn't matter at all because our power is not so huge. So in engineering stage, we disassemble these 3 different things. PID, heater control, and power assembly. These should also be included as well, but the key is that we have all the codes already. So I don't really include that. And the reaction assembly and printing assemblies. And then the PID control, it has been achieved like a few months ago, thanks to Darwin's code, and it just migrate a bit. The second part is the printer and the stage assembly, which is basically something from Carousel. I bought it like in late August, which is pretty nice, $99. And the third one is Ali is currently building and finalizing is the rig for the cooling system. So the hardware is mostly done, and the software is currently ongoing, and also the integration will come a bit later. So that's all.
Quick, Ivan, this setup, has it already been moved to 0110 or it's still in the same room?
It's still in the same room. I think everything Ali has is currently in the same room. 0110 is still not empty.
It's not empty, you mean?
I mean, it is empty. I mean,
Can't occupy it, you mean? Not yet.
Not yet. We still need a ribbon cut event, man.
Oh,
You must
I
be
mean,
present.
you guys just
You
move it.
must.
No, you just start working. You can do the ribbon cutting later. Okay. I mean, okay, one thing I will suggest is you can think with Ali, and this itself is good IP because nobody has done substrate deposition, aerosol. So what is the proof of concept? Apart from, see, you're taking 2 steps, right? One step is this aerosol deposition. Yeah. And then the second step is actually catalysis, you see? So there are 2
Yeah, I
steps.
understand.
So what is
I
the
would say
paper that we can write on just this that beats the state of the art? And what do you want to demonstrate? Do you want to show good mixing of high density on the surface? Do you want to show that you can achieve Janus nanoparticles? So it's good to think about that.
Yes, I fully agree with you. And eventually, what I really want to offer with this is that I need to test how much throughput it can do. Say,
Yeah.
if it can achieve like say 100 grams or 200 grams per day, then we can commercialize it as a
Yeah.
competing tool to produce nanoparticles in bulk and can be sold on Sigma Aldrich, which you cannot find anywhere.
Right.
Yeah.
You don't need to have it in the carbothermal. You can just have it and collect all the particles, right?
Yes, I don't need this substrate. I just
Yeah.
need something, a cold trap that is able to help me to collect the substrate. That is even better.
That's right.
Yeah.
So it's worth thinking about that because that will be the first IP you can file, essentially.
Yes, catalysis is basically more for this project, I would say.
Yes, yeah, exactly. Okay,
Yeah,
and for
so
the syringe pumps, did you buy it or what did you guys do?
syringe pumps, currently I'm using the old syringe pumps.
Yeah, there's a lot in IMRI, by the way. We have like
There are also a lot in CARES. They're like an array of 4x4.
Okay. Okay.
It's almost like a Konami.
Okay.
The current syringe pump I steal it from Nippon Group.
Okay. Okay. All right, guys. I need to step off for this other meeting. Thanks for
Yeah.
presenting.
Is that flow in a vacuum, Ivan?
No, it's in the argon glove box.
Okay.
No, it's not in the argon glove box. It's in the argon flow box.
Okay.
Can we just reconvene at 11 unless someone wants to present something while I'm not there? Sorry, because I have to take this call. It came last minute. Yeah.
Yeah,
I won't be
maybe
online.
let's just
Hmm.
reconnect at 11.
Okay, just reconnect on this group at 11. Okay.
Yeah.
Yeah.
Sure.
See you guys.
Yeah, see you guys.
See you.
All right, so see you guys later at 11.